Hello, our names are Vincent and Henri, and today we'll be discussing x86, a brief guide about Intel's early instruction set architecture. First of all, what is x86? x86 is a family of backwards compatible assembly languages with some level of compatibility dating back to the Intel 8008 released in 1972. It is a low-level type of programming, meaning that there is a strong link between a program's statements and the computer's architecture and machine code instructions. Low-level programming languages run on instructions, and commands or functions in this low-level language map closely to the processor's instruction set. Here, the word low means that there is little to no separation between the language itself and the processor. Second-generation programming languages or assembly languages typically code programs in assembler, which then generates machine code to be executed, since machine code is the only language computers can understand without any processing. Every instruction is represented by a mnemonic, which is a name assigned to a machine function or an abbreviation for an operation. Each mnemonic represents a low-level machine code instruction or opcode in assembly. Add or CMP are examples of mnemonics. In x86, we have two main syntax branches, the Intel syntax and the AT&T syntax. Intel syntax is more dominant in the Windows world, while AT&T syntax is dominant in the Unix world. Here's a summary of the main differences between both. In AT&T syntax, we place the source before the destination in every instruction, while in Intel, we place the destination before the source. Furthermore, with AT&T syntax, every mnemonic is followed with a letter indicating the size of the operand. For example, we have Q for keyword, W for word. While in Intel, we don't do that. Finally, in AT&T syntax, immediate values are prefixed with a $sign, while registers are prefixed with a percentage sign. In Intel, the assembler automatically detects the types of symbols, whether they are registers, constants, or anything else.
And now when it comes to registers, x86 processors have a collection of registers available to be used for storing binary data. Collectively, the data and address registers are called the general registers. Each register has a special purpose. Registers in assembly programming can be considered to be the global variables we use in higher level programming languages for general operations. There are different types of registers. First, we have general purpose registers such as EAX, EBX, ESP, and EBP. Then we have segment registers such as CS and CD. And finally, we have control registers such as EIP. These are some of the general purpose registers in x86 architecture. Each of them has the capability of storing 32 bits of data. The lower part of EAX is called AX, which contains 16 bits of data. AX is also further divided into two parts, AH and AHL, each with 8 bits in size. We can say the same about EBX, ECX, and EDX. EAX, which is the accumulator register, is used for storing operands and result data. EBX, which is the base register, points to the data, and ECX, which is the counter register, is used for loop operations.
Unlike the registers we saw before, the ESP, EBP, ESI, and EDI registers cannot be divided in small sizes of 8 bits. They are divided in upper and lower 16 bits. Since registers in a CPU are limited, they can't be used to store larger chunks of data. That's where memory comes in. Since data can be stored in memory in a stack data structure, the ESP register serves as an indirect memory operand that always points to the top of the stack, while EBP always points to the base of the stack. Furthermore, the ESI and EDI registers can be used for indexing. In x86, memory is accessed either with loads and stores or through push and pop operations. Here we can see the general memory hierarchy of a computer. The registers are at the top and are the fastest when it comes to accessing speed, but they are the smallest in size. Moving down the hierarchy towards the cache, main memory, and disk storage, we can see that while storage size increases, accessing speed decreases. There are several ways data types can be stored, but the two most common ways are little endian and big endian. Little endian data storage type stores the bits in order and is generally used in Intel-based processors, where the main focus is the processing speed and not the amount of power consumed. However, for mobile devices, where battery and power consumption plays an important role, big endian is used.
Let's look at memory segments. The text segment contains the different instructions. The data segment contains data used in the program. The entry point of any program is a global variable called _start. That's where the program execution starts. The text section contains the instructions to print and exit the program, and the data section contains the message string to be printed. One of the most important registers in x86 assembly is EIP, since assembly instructions are written in orderly fashion. For example, in the following program, before the first instruction is executed, EIP points to its address. After it is executed, EIP is incremented by 1 and will point to the second instruction.
The JMP instruction is like the goto function in C. It jumps to the specified location or address without any conditions. In this code, the first and second instructions are executed one after the other, placing the value 4 in ECX and EDX. When the JMP5 instruction is encountered, the program jumps to instruction number 5 and 4 won't be executed. The fifth instruction will compare ECX and EDX by subtracting one out of the other and seeing if the result is 0. If it is, then both values stored are the same and the flag will be set to 1. After that, we encounter JE, which is an instruction similar to BEQ or branch if equal in MIPS, and we'll check for the flag of the previous instruction. JE simply means jump if equal, so if ECX and EDX are the same, then the program will jump to the given function.
The user can use a system call to interact with the operating system by invoking an interrupt. That interrupt will then move to the interrupt handlers table, which then calls the system call handler, which finally invokes the system call routine. There are two ways of invoking a system call. We can use int 0x8 or syscall. To write a system call, we first store our syscall number in EAX. Then store the file descriptor in EBX. We'll use ECX to point to the string that will be printed. Finally, EDX will contain the length of the data that we need to print. After storing those values, we can invoke the interrupt with the function int 0x80.
Let's try to write a simple program that will print the string hello world. First, we declare start as our global variable. Then we start the text section with .text. We then push the syscall number, which is 4, into the EAX register, and file descriptor number 1 into EBX. Then we use ECX to point to the message in the data section. We push the value 12 in EDX since we want to print 12 bytes of data. Then we call the interrupt, which will print hello world. Finally, we push 1 into EAX, which is the syscall number for exit, and we push 5 into EBX since we want to exit with status code 5. And then we call 0x80 to execute. In the data section, we store the message hello world, which will be printed by the program.
Thank you for listening to our presentation. We hope you enjoyed it.